In the first 3 episodes of this series, we built the sensor and motor layers of a voice agent. Episode 1 was the real-time TTS layer, a bidirectional WebSocket pipeline that gets the audio from LLM output in under 200 milliseconds. Episode 2, the telephony bridge, handling PSTN codec chain, acoustic echo cancellation, and choice between video media streams and conversation relay. Episode 3, the multi-modal vision layer, generating unique character voices from images using 11 Labs voice design IP. What we have not built yet is the brain. The part decides what the agent does next, manages state across a multi-turn conversation, handles interruptions gracefully, and delegates subtasks to specialist sub-agents. That is this episode. We are going to use LangGraph to build a supervisor orchestration pattern for a voice agent. We add Redis checkpointing so agent can save and restore state in sub-millisecond time. We implement Barge-in logic, the ability to detect when the user interrupts and roll back agent states to the point of interruption. And we add 2 latency tricks: Speculative TTS execution, which starts audio generation before the full LLM output is ready, and Semantic caching in Redis, which short-circuits the LLM entirely for high-frequency queries. This is the architecture that separates a demo from a production voice agent. Let us build it. Let me start with the core problem. Why stateless agents fail in real conversation? Here is what happens in real conversation when the user interrupts. The agent is in mid-sentence. The user starts talking. In a well-engineered system, the agent detects the interruption, stops speaking, and responds what the user just said. In a naive system, one of 3 things happen. The agent finishes its sentence regardless. The user has to wait. The agent stops but loses all context about what it's saying. The conversation becomes incoherent. Or the agent crashes entirely because its state machine does not have a handler for interrupted case. All 3 outcomes are bad. They are all caused by the same root problem. State is not being managed explicitly. In a stateless agent, each LLM call is independent. There is no record of what the agent was about to say, what the tasks are in flight, or what point in conversation the interruption has happened at. You cannot roll back a previous state because there is no state to roll back to. LangGraph solves this with an explicit state graph. Every node in the graph reads from and writes to a typed state object. Every state transition is a graph edge. Every state is checkpointed, saved to a persistence store, so you can rewind to any point in the conversation history and resume from there. For a voice agent, this means when the user interrupts, we load checkpoint just before the interrupted utterance, update the state to reflect the interruption, and continue from there. The agent picks up thread correctly. Let me show the full architecture before we build it. The architecture has 3 layers here. The voice layer is what we built in episodes 1 through 3. The 11 Labs WebSocket for real-time TTS. The video bridge for telephony. The vision pipeline for multimodal character generation. In this episode, the voice layer is consumer of the orchestration layer. We do not change it. The orchestration layer is LangGraph. Supervisor node is the top-level decision maker. It receives the user utterance, decides which subagent to delegate to, booking, lookup, escalation, or general conversation, and assembles the response. The supervisor reads from and writes to the shared voice state. The state layer is Redis. LangGraph's checkpoint interface connects to Redis, storing the full voice state after every node transition. The voice state is a type dictionary containing the current utterance, the turn history, in-flight tasks, and checkpoint ID from the last completed turn. Voice state loads in under a millisecond even for long conversation histories. 3 layers. Clean interfaces. The voice layer streams audio. The orchestration layer runs the graph. Redis presses the state. Let me start with the LangGraph supervisor pattern. The supervisor pattern in LangGraph is a routing architecture. Supervisor is a node that receives the full conversation state and decides which subagent to call next. In supervisor PY, the supervisor node uses small LLM call to classify the user intent into one of 4 categories, like booking, lookup, escalation, or general. Based on that classification, it routes to appropriate subagent node. Each subagent does its work, querying a database, calling an external API, or generating a response, and writes its output back to the shared state. Control returns to supervisor, which assembles the final response from the subagent output. Why a supervisor instead of single LLM call? Two reasons. First, specializations. A booking subagent can be given a focus system prompt with booking context, a slot filling pattern, and guardrail specific to reservation. A lookup subagent can be given database schemes and query templates. Each subagent is better at its task than a single general purpose LLM call would be. Second is the observability. Every routing decision and subagent call is named node in the graph. You can see exactly which path a conversation took, at which node it failed, and what state it was in when it failed. This is invaluable for debugging production voice agent. The VoiceState TypedDictionary is the data contract between all nodes. Every node reads from the same state object and writes back to it. No hidden context, no global variables. Let's go to the Visual Studio and see. Let's go inside episode 4, voice state with current utterance, turn history, active task, and checkpoint ID. Let's go to the supervisor PY. This is the supervisor node with intent classification and routing state update. Here. And here classify intent, and here route after supervisor. And finally build graph. LangGraph state graph with add node, add conditional edges, and adding edges. If we go to the tests, coverage for routing and graph invocation. Let me run the supervisor PY. The expected output shows the booking utterance routed to the booking agent with intent, active task, turn history, and agent response. Now let me show how Redis checkpoint enables Barge-in. LangGraph has a checkpoint interface, an abstract class with two methods, put and get. You implement these methods against your persistence storage, and LangGraph calls them automatically after every node transition. In Redis checkpointer PY, we implement the LangGraph checkpointer interface using Redis. After every node transitions, every time a subagent writes its output, LangGraph serializes the current state to the JSON and calls put with thread ID and the checkpoint ID. Redis stores it in a hash with TTL of 1 hour. The critical property of this approach is read latency. A Redis get on a local instance takes under a millisecond. On a managed Redis class instance in the same region as your application, it takes 2 to 5 milliseconds. This is fast enough to use in a real-time path of a voice conversation. Compare this to the database back checkpointing, where a read might take 20 or 100 milliseconds, or to in-memory checkpointing, which does not survive process restarts or horizontal scaling. For Barge-in case, we call get with the checkpoint ID from the moment just before the interrupted utterance began. We get back the full conversation state as it was at that point. We update the state to indicate the interruption, clearing the in-flight TTS, updating the turn history, and continue the graph from the supervisor mode. The conversation picks up correctly, no lost content. Alright, let me show the put and get overloads in the Redis checkpoint PY. Here they are. Alright, if you go back to supervisor PY, here is the graph to compile the checkpointer. If you go to Barge-in PY, as you can see here, checkpoint read and resume and invoke. Now let me show the Barge-in logic itself. Barge-in detection is the mechanism that tells the system the user has started speaking while the agent is still talking. The implementation has two parts, the detection and the rollback. Detection happens in voice layer. The 11 Labs WebSocket API sends a user audio event whenever the STT subsystem detects user speech. In Barge-in PY, we listen for this event and compare the timestamp against the timestamp of last agent utterance start. If user speech begins while agent audio is playing, we raise a Barge-in detected event. The Barge-in detected event triggers 3 actions. First, we stop current TTS stream. We send an interrupt signal to the 11 Labs WebSocket, like a clear audio or stop event, which causes the agent to stop speaking immediately. Second, we perform state rollback. We call Redis checkpointers get method with the checkpoint ID from the start of the utterance was interrupted. This gives us the state as it was just before the agent began speaking. Third, we inject the interruption context. We add the partial user utterance, what we heard before they stopped, to turn the history. Marked as an interruption, we update the state's current utterance field with what SSD committed from the Barge-in audio. Then we re-enter the graph from the supervisor node with the rollback state. The supervisor sees the interruption event and rolls accordingly, like typically to general sub-agent to acknowledge the interruption and respond to what the user actually said. Get the handle user audio event. Now does timespan overlap check and raises Barge-in detected. Now implements 3-step rollback, stop TTS, get checkpoint, inject interruption context. Resume from Redis checkpoint, remains the checkpoint read and resume path. If you go to Barge-in live demo py, new runnable live demo script showing with response, interruption behavior and resumed response. Let's try the demo. Look, agent starts with multi-sentence output, user audio events arrive with timestamp and energy here. Barge-in detected is raised here. And rollback steps, stop TTS, get and deserialize the checkpoint, inject interruption, context. Now let me show speculative TTS execution. How we start audio generation before the LLM is done. In a streaming LLM response, tokens arrive at a time. The LLM's first sentence is usually available long before the full response is complete. Speculative TTS exploits this. Instead of waiting for full LLM response before starting TTS, we start generating audio as soon as we detect the first sentence boundary in token stream. In speculative PY, we stream the LLM output token by token. We accumulate tokens until we detect sentence boundary, a period, question mark, or exclamation mark followed by a space of or end of stream. When we detect the boundary, we fire the first chunk of text to the 11 labs TTS WebSocket. We keep accumulating tokens for the second sentence and fire that chunk when it completes. This continues until the LLM response is finished. The user hears the first sentence while LLM still generating the second. The perceived latency is the time to the first sentence boundary, typically less than a second, not the time to full response. The speculative pattern introduces one complication, the cancellation. If the user barks in after we started TTS for sentence 1, we need to cancel any queued TTS for sentences 2 and 3. We track in-flight TTS tasks in VoiceState and cancel them during the Barge-in rollback. Let's go to the speculative PY, get the token accumulation loop and boundary check. If we run speculative latency demo PY under the demos, we can see the timing and improved first audio. Let's see. Look at the speculative TTS latency demo. Total tokens 24, total token interval 40 milliseconds. TTS dispatch overhead 25 milliseconds. So look at the latency improvement, 520 milliseconds. This is an example. And this is the voice state that we used. If we want to again run the Barge-in demo, compare like this, and we see the cancellation follow also. Now let me show the last latency optimization, semantic caching. Some queries in a voice conversation are highly repetitive. What are your hours? Where are you located? What is the price? Something like that. These queries arrive in different parsing, but with the same semantic intent. Semantic caching short-circuits the LLM for these queries. We embed the user's utterance and compare it against a set of pre-cached query embeddings using cosine similarity. If the similarity exceeds a threshold, for example, we use 92%, we return the cached response directly, bypassing the supervisor and all sub-agents entirely. In semantic cache PY, the cache is backed by Redis as a hash of embedding vectors and their cache responses. One each new utterance, we embed the text using OpenAI's text embedding tree small model and run a cosine similarity check against the stored embeddings. A cache hit returns in 10 to 30 milliseconds compared to 500 to 1500 milliseconds for a full LLM round trip. We call this the fast talker. Queries that the agent can answer before the user has finished speaking effectively. The cache is populated manually for high-frequency queries before the agent goes live. Over time, you can also promote frequently asked queries from the conversation logs automatically. For example, a simple background job that runs nightly. Alright, let's see the semantic cache live demo. In this demo, we need to see 3 different parsed questions, all produce cache hit, as you can see here. And terminal needs to print similarity score and pre-query latency so we can show speed up clearly. Let's run this demo like this. Look, cached score. What does this Roman statue represents? Score is 1. The second question, can you explain the meaning of this Roman statue? Score 66. And again cached. Score 45. The question is, who is this Roman figure meant to be? These are the same question in 3 different parsings. And watch the semantic cached all 3. As you can see, the latency difference in the terminal log there. And the answer is same for each one. Let me bring the full pipeline together with end-to-end demo. Let me run the complete system end-to-end. The setup. The voice agent is running with the LangGraph Supervisor, Redis checkpoint, and 11 Labs voice layer from episode 1. I am connected via web client from episode 1. First, I ask a question. The semantic cache handles, what are your opening hours? The response comes back in under 30 milliseconds. The cache, no LLM call. Second, I ask a booking question. I would like to book a table for 2 on Friday. The supervisor routes to the booking subagent. The subagent runs a slot flipping loop. What time on Friday? I respond 7:30. The booking subagent confirms. Third, interrupt the agent mid-confirmation. While agent is reading back to the booking details, I say actually make it 8 o'clock. The barge-in triggers. The agent stops mid-sentence. The state rolls back just before the confirmation began. The supervisor receives the interruption. Context routes to the booking subagent with the updated time. The agent responds, of course, updated to 8 o'clock Friday. Shall I confirm? The conversation is coherent. The interruption was handled cleanly. That's the full pipeline. Semantic cache for instance responses, LangGraph Supervisor for routing, Redis checkpointing for rollback, Barge-in detection for natural interruptions, and Speculative TTS for perceived responsiveness. To make a demo, we need to run a Redis on our Docker desktop first. I think now we have the Redis up and running. Let me run the command Barge-in live demo, no pause, Redis URL, or is localhost.
In this architecture, the supervisor routes requests by intent. We checkpoint state before each major generation step. General agent, I can answer the question directly or route to a specialist.
Yep. Let's test Barge-in.
In this architecture, the supervisor routes requests by intent. We checkpoint state before each major generation step. General agent, I can answer the question directly or route to a specialist.
Alright, while this is happening, we will open another terminal, and at that moment we will Redis CLI monitor here. Oops. So, because it's in Docker, we need to Docker. Alright, and let's go back to first terminal and run the demo again.
In this architecture, the supervisor routes requests by intent. We checkpoint state before each major generation step.
As you can see, now he
General
gets
agent,
happening.
I can answer the question directly or route to a specialist.
We see HSET, expire, and get live in the pane 2, while Barge-in recover audio plays in pane 1. Let me close with the 4 patterns to carry into your own production voice agents. 4 things to take from these episodes. 1. State is foundation of Barge-in. You cannot implement natural interruption handling without explicit state management. LangGraph's typed state graph and checkpointer interface give you the tools. Redis gives you the speed. 2. The supervisor pattern scales. Starting with 4 subagents, you can add more without changing the supervisor's routing logic. New domain, new subagent node, new edge in the graph. The pattern absorbs complexity without breaking. 3. Speculative TTS is the perceived latency trick, not a real latency trick. The LLM still takes the same time, but the user hears audio sooner, before the full response is generated. For voice, perception is what matters. 4. Semantic caching should be your first performance investment, not your last. For high-frequency queries, a 30 millisecond cache hits beats a 1000 millisecond LLM call every time. Build the cache before you optimize the LLM calls. This is the final episode of Architecting Production Voice AI series. The full code is in the description. All 4 episodes is in the Voice Agent Architect Lab repository. Links in the description, as I said. The unified Voice Agent template on the main branch shows how the modules from all 4 episodes compose into a single production system. Thank you for building this with me. If you like this, please like and subscribe. Thank you guys.